the spring constant of this spring. What does m stands for? M is the mass of this object. So we have 2 pi divided by the period equal to square root of k over m. Can you solve for t from here? What is t equal to? Well, I'm going to simply give it to you. I want you to solve it on your own. Solving for t gives me t equal to 2 pi times square root of m over k. Now, this is the equation for the period of oscillation of a loaded spring. That means the period of oscillation of a loaded spring like this is given by this equation, t equal to 2 pi square root of m over k. That means the period depends on the spring constant and the mass. Okay, and again, that is an important equation. T equal to 2 pi square root of m over k. Let's now talk about simple pendulum. A simple pendulum. Have you seen a simple pendulum? What is a simple pendulum? A simple pendulum is something like this. Can you see this here? A mass suspended by means of a string. If I pull the mass to one side and leave, you see what happens. The mass oscillates. And this oscillation is also simple harmonic. And this is called a simple pendulum. In fact, I don't know whether many of you remember, in the olden days, clocks used to run on a simple pendulum, oscillations of a pendulum. It was very widely used. The electronic age has actually taken away that beautiful pendulum clock. Well, anyway, the oscillation of a simple pendulum is a good example of a simple harmonic motion. A pendulum consists of a hanging mass from a string attached to a support at point O. There is the support and a string hanging from the point O, and the mass is attached to one end. A represents the equilibrium position. Now, this is the equilibrium position of the mass. The length of the string is L. When the bob, you see this mass is called the pendulum bob. When the pendulum bob is pulled to one position, what happens? When I pull it to the side and leave it, you see, when you raise it to one side, you give it potential energy. And because it has potential energy here, it's going to fall back to the equilibrium position. And when it comes back to the equilibrium position, it has acquired velocity. And that velocity will make it climb to the other extreme, like a swing. You see that? Just like the energy changes in the oscillating spring, here again we have energy changes. There, when the mass is pulled to one side, to position B, the string makes an angle theta. Now, just like the spring has a restoring force pulling the object mass, pulling the mass back to the equilibrium position, here again there is a restoring force, which is the component of the weight pulling it back to the equilibrium position. Alright. If m is the mass of the bob, its weight mg acts vertically down. Is that right? If m is the mass of this bob, its weight mg will be acting vertically down. Now, this weight has two components. mg cos theta, well, this is the tension on the string. Now the component of the weight mg cos theta in this direction balances the tension on the string. There you are. Now this angle will be the same as that angle theta. So this is the weight. The component of that weight in this direction will be mg cos theta. This is mg cos theta, which balances the tension on the string. And the component of the weight mg sine theta, look at this component, mg sine theta. What is the function of that? That is the restoring force. That is the force pulling the pendulum bob back to the equilibrium position. So mg sine theta provides the restoring force, pulling the mass back to position A. So when you, now watch here, when you pull the mass to one side, what happened? There is a force pulling this mass back to the equilibrium position there. That's why it comes back. So this mg sine theta is that restoring force. And this produces an acceleration. It makes the bob accelerate towards the equilibrium position, so that when it reaches the equilibrium position, it will have a maximum velocity. And this mg sine theta is the net force producing the acceleration on this mass, so that mg sine theta equal to negative ma. Now why is it negative? Because the acceleration is opposite to the displacement. Alright, now we can see m and m will cancel, and solving for a gives you a equal to negative g sine theta. This a is the acceleration produced on the pendulum bob by the restoring force. So a equal to negative g sine theta. Well, let's now get a reasonable approximation for this sine theta. The distance from A to B is the displacement of the mass. Is that right? The mass has been displaced from A to B, that distance. I'm going to call that distance x. When the amplitude of oscillation is small, this displacement is approximately equal to x, so that sine theta equal to x divided by L. You see, L is the length of this string. Sine theta equal to x over L. This is the sine theta. Sine theta is opposite side divided by the hypotenuse. So sine theta equal to x over L, which is an approximation. It works only when this angle theta is very small. If the angle theta is large, that approximation is a very poor approximation. Alright, now if you replace sine theta by x over L, can you now rewrite the equation for acceleration? The equation for acceleration now becomes negative g times x over L, where x is the displacement, L is the length of the pendulum. Alright, do you now recall the equation for acceleration we developed for simple harmonic motion? What is the acceleration for simple harmonic motion? Do you see I rewrote this equation as negative g over L times x, where what does x stands for? The displacement. Alright, but acceleration for a simple harmonic motion, I was asking you that question. Do you remember the equation we developed for acceleration of a simple harmonic motion? I know most of you forget all these things very easily. Acceleration A equal to negative omega squared y. There you are. A equal to negative omega squared y. We are now going to compare these two equations. Look at this. A equal to negative G over L times X. What does this X stand for? Displacement. This is for the simple pendulum. And this is a general equation for acceleration of any simple harmonic motion. A equal to negative omega squared y, where y is the displacement. So X and y are both the same. That means if you compare the two equations, this G over L for the simple pendulum stands for this omega squared. Don't you see it? Alright, comparing these two equations, we have omega squared equal to G over L. Now remember that X and Y both stands for displacement. Therefore they are the same. Omega squared equal to G over L. Do you recall what omega is? Can you write omega in terms of the period? Yes. Omega is 2 pi divided by t. Omega squared is 4 pi squared divided by t squared. Alright? Can you solve for t from there? 4 pi squared over t squared equal to G over L. Can you solve for t squared from this equation? Well, t squared equal to 4 pi squared times L over G, and take the square root of that. T equal to 2 pi square root L over G, and this is the equation for the period of a simple pendulum. So I want you to now go back and tell me what is the period of oscillation of a loaded spring that we developed. Well, we developed an equation for the oscillation of a loaded spring. What is the equation for the period of oscillation of a loaded spring? T is 2 pi square root m over k. Alright, look at the period of oscillation of a simple pendulum. T equal to 2 pi square root L over G. They are similar, is that right? Alright, you must be familiar with these equations. Let's now talk about another type